Let's talk a little more about power when it comes to resistors. Oftentimes we'll see this as power dissipated by a resistor or in a resistor, though by a resistor's better. That terminology is because resistors convert energy, specifically electrical energy, to other forms. Other forms. So, for example, a light bulb. Now, a regular light bulb, not a LED light bulb. An LED, we of course get light. A regular light bulb that we can model as a resistor, it produces light, which is a form of energy. They are electromagnetic waves. But it also produces thermal energy. Light bulbs would get warm while they were on. So the electrical energy is being converted to other forms. Your toaster, if you have one, it creates thermal energy, which in turn can toast your bread. So, wide variety of applications of resistors. Ultimately, they're converting energy from electrical form to some other form. So we can't talk about energy stored because they're not storing any energy. But we can talk about how fast that energy is being converted. And we do that in terms of power. Now I'm going to put a subscript of R on this for specifically the resistor. So the power dissipated by a resistor. One way we can write this is in terms of the current and the potential difference across the resistor. But we know delta V for a resistor is also I times R. So, for example, we could write this. If we plug in I times R for delta V, the power would become I squared R. So we could write it in terms of current and resistance. Similarly, if we solved for I and plugged it in, so I would be delta V over R. The power we could write as delta V squared over R. So the power dissipated by our resistor can be written in terms of any two of these three values: current, resistance, and potential difference. The units, well, power is in watts. So we will see W, which if you've ever gone to buy a light bulb, 60 watts, 100 watts, you're buying what they're rated at in terms of the rate at which they can convert the energy. We know watts is a joule per second, but in terms of this equation here, this is also going to be an amp times not an ohm, and volt. That's based off of the first, current times voltage. That would also be amp squared times ohms, based off of this second one, or volts squared over ohms. So any of these are going to result in a watt. So the rate at which energy is converted from one form to another. We can find this power fairly easily if we have a battery, for example, and we connect this battery to a couple of resistors. I'm going to just make these 6 ohm resistors. Now, in terms of how these resistors are connected, as soon as there is a closed complete circuit, current will flow because this current has no option to go through different paths, these two resistors are connected in series. In series, we simply add the values of the resistors together to get an equivalent resistance. And so this circuit would be equivalent to having one resistor that's 12 ohms. The current then we can find that would flow in this circuit using Ohm's law up here. The current that would flow would be the potential difference across that equivalent resistance divided by the equivalent resistance. But from the going around the loop, if 12 volts is supplied by the battery and this resistor is the only element in the loop, it must have the entire 12 volts that the battery is supplying across it. So 12 volts divided by our 12 ohms, the current flowing through this circuit would be 1 amp. Let me make that look more like an A. So if we wanted the power dissipated by the circuit as a whole, so dissipated in the circuit, we can simply look at this equivalent to calculate that. Whereas we'll go back and look at the power dissipated by the individual resistors as well. So in the situation where we want to know the power dissipated in the circuit as a whole, we can look at this total current that is flowing and then multiply by the equivalent resistance, which we found is 12 ohms. So this particular circuit would dissipate 12 watts. So 12 joules per second. Now that's not a whole lot, but that's based off of these values that I've chosen to use. In our problems, we're going to assume the batteries are capable of pushing out the needed current, of causing that current to flow. In reality, when you hook up a circuit, the battery might not be strong enough to push out as much current as you need. We are also assuming ideal wires in that the connecting wires themselves have no resistance. So all of the energy is being converted by the actual resistor. So 12 watts in this equivalent circuit. If we work backwards, now remember these two resistors were connected in series, which means they must have the same current flowing through them. And they have the same current as their equivalent resistance. So we calculated that current to be 1 amp. That means I can come up here and say that there is 1 amp flowing through this circuit. So each of these individual resistors has 1 amp flowing through them. So the power, I'm going to just use I squared R again, but I need to use that for these individual resistors. So 6 watts on this top resistor and 6 watts on this bottom resistor, which 6 plus 6 adds up to be the 12. Now in this particular case, they have the same power because they also have the same resistance. So these, if they happened to be light bulbs, they would be equally bright. But if they were not the same, let me slide this to the side a little bit, and let's make a circuit that is similar. I'm not sure why I'm drawing 2 lines for the battery instead of just 1. Still just means the battery. Let's start with our 12 watts and our 6 ohms, but let's do 8 ohms so that they are different. They're not different by much, but they are different. We can still treat this as an equivalent, batteries are not watts. 12 volts for our battery. We can still get an equivalent resistance, and since these are in series, we still just add them together to find their equivalent. So 6 and 8, this would be a 14 ohm resistor. The current that would flow through this circuit we can calculate with delta V over R equivalent. So 12 volts over 14 ohms. So the current is different simply because the equivalent resistance is different. So we have less current flowing this time, which hopefully makes sense because we have a larger equivalent resistance. The amount of current that flows in a circuit is always dependent on the voltage supplied and the equivalent resistance. If we change the equivalent resistance, that changes how much current can flow. Now we can take this back. Since these are in series, these both individually will have this 0.857 amps flowing across them, or flowing through them, I should say. So power, I'm still using I squared R. So for this top one, 0.857, I'm going to square that and then multiply by the 6 ohms. I get 4.4 watts for this top resistor. That's less than it had over in this first example over here, but that's because we had more current. In this first example, we ended up with 1 amp of current, and that's because we had a smaller equivalent resistance. The power for this second resistor in our new example would be the same current times the 8 ohms. Well, the current squared. I'm getting 5.9 watts. So this 8 ohm resistor has a larger power because it has the same current as the 6 ohm resistor, but it also has a larger resistance. So power is not terribly difficult to calculate. Conceptually, we have to remember that, well, we have to remember series versus parallel. We have to remember what they have in common. In series, our resistors have the same current. In parallel, they have the same voltage. And the overall current that flows in a circuit is completely and totally dependent on the equivalent resistance of the circuit as well as the battery voltage. So any problem we see, we need to be thinking equivalent resistance. Now, in terms of conceptually understanding power, we can think of these, for example, as light bulbs. You will see a number of problems that refer to brightness. These are 2 light bulbs. Which one is brighter? Well, the brighter one just like a 60 watt versus a 100 watt light bulb, the larger the power, the brighter the light bulb would be. So in the second example here, the 8 ohm resistor would be brighter than the 6 ohm resistor. Now, that is not a huge difference in brightness. I don't know if that would be perceptible to our eyes, but technically that is a larger power. If we go back to the first example where both of these light bulbs had 6 watts, these would be equally bright. They would have the same brightness. And so you will see some examples, or some questions, I should say, throughout your homework. And I'm going to do some conceptual questions next as well, to think about brightness, to think about power and current through resistors.